the class project overview for Introduction to SWI-Prolog. Okay, so once upon a time there was a brave little girl named Alice, and one day Alice baked a fresh pie to give to her grandmother who lived in the woods. Our class project is going to be to build, each of us build a tool that helps parents generate bedtime stories. And those bedtime stories, and then in its final form, we'll have a web application that you can run on the web and hand out bedtime stories to people that they can customize with their child's name and their favorite plushie or teddy bear, and that'll be the final form. What I'm okay. We have a little start of a story here. What do you imagine happens next in the story? People will answer in chat. I'll wait. Kind of things might happen. Anybody going to answer? Okay, well, what kind of things might happen? Well, it's the nature of the story. We know it's a children's story, so probably nothing too terrible. But Alice is going to encounter problems in the process of giving her the pie is covered with flies. Right. Alice is going to encounter problems getting her pie to her grandmother, right? So Alice has a plan. Alice may get lost in the woods. Alice may Alice's pie may get covered with flies. Alice may encounter a wolf. And then Alice will find some way out of her difficulty. That's the nature of a story. Is get your protagonist in trouble. Our protagonist is Alice in this case. That's your main character. And then get her back out of trouble. That's actually an algorithm of a sort. Okay. All right. We're going to do this in 3 phases, and I suspect people may still be working on it after the end of week 3, but we're going to introduce it over 3 weeks. The first step is Alice needs to have a plan. In this case, her plan is bake a pie and give it to her grandmother. Her grandmother is there'll be some steps involved in that, and we will build a tool to generate those steps. So in this case, the steps would be something like take flour and turn it into dough, and take berries and clean them and roll out a pie crust and bake the pie in the oven, and then and then take the pie into the woods, and then take yourself and the pie from the woods to Granny's house, give the pie to Granny, come home, come back to the woods, and then come home, right? So that's a plan. And gosh, that sounds like something we can find a route, right? This is not all that different than like route finding or your trains exercise. Okay? An awful lot of things in Prolog end up looking like the trains exercise. Now, that's really just a plan. We want a story, so we have to have things go wrong. So we will take our plan, and then we will use it to have a story generator that'll make things go wrong, and then we'll get ourselves out of it. That'll be week 2. And then our last week, we will, or our last section will be that we'll put it onto the web as a web application that you can run. Prolog runs as its own, SWI-Prolog web applications run as their own web server. They're not in a container. And so a very typical configuration, just because Apache's very good at doing all this stuff and reliable. A very typical thing is to front it with Apache and use a vhost file to forward requests to a high port, and then have the Prolog only respond to localhost. But yeah, you'll be able to run on your local machine, and if you have a public URI, you'll be able to put this up. So that'll be what we'll build at the end. Okay, so the planner. Sorry, I had those out of order. Okay, so first thing is we have to have a plan. So we need a planner. The planner is going to have some set of initial conditions wherever we are when we start, and then some set of goals, and often there are positive and negative goals, and then there are and then you provide a set of actions, and then basically we just do a tree search through the actions. We try one action, then we try another action, and we try another action until we reach the goal. Okay, everybody following me along? Following along with me. Okay, so what's in an action? Well, this is the classic strips planner. Is that there is a set of things that must be true in your current state before in order to apply this action. That is, if the pie is in the kitchen, you can only pick up the pie if you are in the kitchen. Negative prereqs, well, if you only allow carrying one thing, then you can't be carrying anything at the start of this action. And then and then you might add, and then there's going to be a set of new things that will occur. You're carrying the pie, and a set of things to remove, that your hands are empty, or if you bake the pie, you use up the berries, and you'll have a set of those. And then typically you'll want to have some kind of English description with it, so that when you finally print out your answer, you get a story and not some prologue term. And here I have represented my description in a way that's pretty common in prologue for holding on to these kinds of things. I have this was actually taken from something that was part of a rule. I have this minus operator, which I'm just using to hold two pieces together. And the left-hand piece is a format string to be passed to the Prolog library predicate format, format 3 probably in this case, because of wherever we're writing it, or format 2. And this is then all of the arguments that go along with it. Prolog has no var arg, but it's easy to turn a bunch of arguments into a list. So that's the typical way of handling, what in C would be a var arg. And so now we can just simply look for actions that fulfill the positive and negative prerequisites and try them, and then try wherever it leads us, and just keep looking. However, we should think about this. Clearly, for example, my test file of my version has, Alice can walk to the woods, but then Alice can walk from the woods to her house. And so Alice could ping pong back and forth. So we might not want to just do depth first search, right? We don't want to always be trying the first action first. Instead, so here's a tree of states that Alice might visit. Alice starts, and then Alice walks to the woods. I didn't realize this was so low resolution. And then Alice walks on to Granny's, and then Alice gives the pie to Granny, walks to the woods, and goes home. Or Alice is at Granny's, but doesn't go in, just immediately turns around, goes back to the woods, and goes home. And then, Alice could continue back to the woods, back to home, back to someplace else. So this could blow up on us, right? So our strategy for avoiding that is that we will take everything in this top layer, which is the start state, and we'll check to see if we're at the goal there. And then we'll add these two into a queue. We'll maintain a queue. This queue is called the open list, by the way. So we'll, walk to the woods or make the pie are the only options here. So stick those on your queue. And then pull the first thing off the queue and say, okay, where can I go from here? Well, I could go into the woods. I could go back to home. I don't have everything drawn in here because it'd get too bushy. But but one of them is at Granny's, which we know is actually going somewhere, right? And then once we're at Granny's, we can give the pie to Granny, or we can go back to the woods. And so once we're at Granny's, we then, when it gets to the front of the queue, as we're processing things off the queue, we can say, oh, there's Happy Granny. Okay, that's one strategy. Or we can when it gets to the front of the queue, then we add the Happy Granny stage and the in the woods stage. There's another strategy. We can make certain that we never return to the same state. While it's possible to return to the same state in the story, right? Yeah, we have a bushy action tree. Bushy is a technical term. It means that there's a high number of children. So the other thing we can do is maintain what's conventionally called a closed list. And after we put all the children of a state, we take a state, we look and see if we're at the goal, of course. If we're not, then we put all the children on the open list. And then we put the state itself on the closed list. And before we ever put anything on the open list, we make certain it's not on the closed list. So, for example, here, after we've gotten back, now these are sometimes different states, right? Here, this one, Granny has the pie, or Alice has the pie, and here Alice does not have the pie. So, so those are different, and we might need to explore both of those. But if you ever get back to exactly where you started, exactly someplace else, yeah, I can probably do that. The deal is that I lose your chat when I do that. So, because unfortunately, it insists on showing me this help thing in full screen as well. So, okay, that's better resolution, hopefully. So, where were we? We are here. So, we're going to have a closed list. And as we stick more and more states on the closed list, we're going to be pruning away branches that we've already reached by another method. And that helps cut down on this back and forth effect. That is, if Alice goes to the woods, Alice won't go back home immediately because that would return her to her start state. Yeah. Is that clear to everybody? And yeah, I'm going to have to be swapping back and forth to do that, so I'll only do it when I'm showing a diagram. All right, is that clear to people? That's probably the most complicated part of this process. Yeah, I think. Okay, so this is what we've just gone over. When you newly discover a state, stick it on the end of the open set queue. After you've put all the children on the queue, then add the state to the closed set. And before you put anything on the queue, just if it's already on the closed set, discard it. By the way, if it's already on the open set, you might consider whether to discard it. That is, I'm going to explore this, but I reached there by a different method. You might be cutting out interesting stories that way, but okay. And then just keep taking things off the front of the queue. Now, what happens if your queue gets empty? What's that mean? Well, really, that means you can't reach your goal. Okay? This is a trick that can further make things easy. If you are at a dead end, you can have a special token like dead, and if you see that in your state, don't stick it back on the open. Stick it on closed, but don't stick it on open, because, but don't try and get children, because that way you can make something like, I fall off the cliff, then I'm dead, and now we don't have to say for every other state. Yeah, but specifically it makes writing the actions easier, because now you don't have to specifically say you must be alive to perform this action. It's just implicit that if you're dead, you can perform no action. So at that point, you can discard the solution. Okay. All right, that's the planner, and you'll want to decide how you represent actions. How you I used a dict. I used facts, and each fact had a dict in it, and it actually had two arguments. It had one for the name and one for the dict, and that was that worked out fairly well for me. So, but you'll want to decide how you represent the actions, and then how you're going to represent these internal states. And of course, when you store the state on the open list, remember to store the story with it, the story so far, because eventually you're going to need that when you get down to the bottom and return the story. Because it's the story that's in the end what we want, not all the intermediate states. Okay. All right. Way back here at the start, I started talking about what's in a story. And I said, well, what we'll do is we'll get Alice in trouble and then get her out. So for every action, or for many actions, you'll write events. And these will probably be like facts that contain, like the name of the state. I recommend naming your states just so you can, or naming your actions. And then you'll have an event associated with an action, and an event is something like in the write-up, I have the example of Sally goes home, and instead of going home, her plane is grounded by a hurricane. So it's diverted to the romantic city, and that sets up the plot. If Sally, you kind of need to be wise. These things are obviously not going to supply the imagination. You're going to have little bits and pieces of plots, and it's going to string them together. So, you need to provide then some way for Sally to get home eventually. the hurricane just is over, or Sally flies in Mr. Romantic's private jet, or whatever your outcome is. Okay? So, but we said that Alice's start was that Alice makes a plan. She plans to bake a pie and give it to Granny. So Alice makes a plan. Alice then takes that, and we're going to make a plan using a planner. All right. We're then going to simulate this plan. We have to write a simulator that just simply steps through the plan. Well, this wouldn't be very difficult, except at each step, then we'll stop, we'll roll a die, and we'll see if one of these events happen. If the event happens, the event then will have an alternate set of things to add and remove. Okay? So rather than using the ones from the action, we use the one from the event. So Sally, instead of landing in her home city, lands in Romantic City. Okay? People following that? How events figure into this? Now comes the kind of tricky, the trick that makes this work kind of cool. And that is, we take the new set of conditions. Sally is in Romantic City. And we now run the planner again, using those as the initial conditions. So, Sally is in Romantic City and still wants to get home and still wants to find true love. And Sally, encounters romantic stranger and finds true love, but now she still has to get home. Alice meets the wolf in the woods, and now before Alice can get to Granny's, she's going to have to get rid of the wolf. So that's going to require a new plan. So Alice is going to have to go back to her house and get the wolf repellent or whatever. Okay. And then once you have a new plan, then you go back to step 2 and you start simulating again. And probably something else happens and further changes things. And this is basically, every movie ever, every book ever. This is a heist movie, right? We're going to dig a tunnel under the vault and lower the guy down on a wire and do this and do that, and of course things always go wrong. The wire breaks and the guy lands and sets off the alarm. So, and of course you want to usually have some way of getting out that may cause a further complication, but some way of getting out that of everything you get into. Okay? Any questions so far? While I'm waiting for you to respond on the latency, I will say, by the way, I'm hoping that your assignments finally get graded this weekend. We've had a little bit of problem with getting that together. So when we, okay, nobody ever seems to have responded. I will assume there are no questions. All right, so finally, so one other thing that might happen is, think of an airplane movie, right? One of these movies where, you know, that's about, you know, an airplane in trouble. The goal is usually to get back on the ground. Getting on the ground at your destination, you know, the passengers had some destination, but after they're hijacked, getting to their original destination is not their primary goal, right? That's not what's driving the story anymore. It's getting out of the plane, you know, or getting on the ground and away from the plane safely. And so we might want to change the goals. So that's something to pre-plan for. Now, the original formulation had positive and negative goals, and that's an unnecessary complication. You can make a final action kind of a they lived happily ever after goal that just has negative prereqs of you know, you're not, the wolf is not there, and you know, the monster is not chasing you, and the pie does not have flies, and then the positive prereq is, you know, Granny is happy and we're back at home, and then make a final action that says that adds done, and then we can just test for done, and then you can, even if you change the goal, you know, you can make it more than one happily ever after, you know, one of which is you were hijacked, which was just added at the time you're hijacked, and then is always there, and then you remove the you know, you remove the other goals, and you add, you know, just get on the ground and get away, right? And then you can test for that. We're hijacked as a set of goals in the set of things that get you to the happily ever after. Is that clear at all? Okay. Well, that's the end of part 2. That's you know, if you build that, you should be happily spitting out little stories. The last thing we'll do is we'll use some of Prolog's kind of natural language processing, and you'll use probably a DCG and convert your story using into English, and you may do some post processing on the story, and, you know, kind of clean it up, and then we'll put it on the web and let people put in the names of their plushies, or say, I only want my child's particularly afraid. Don't have really scary stories. And you'll just manipulate the initial conditions and probably some translation table, and you do that over the web, so then they can generate stories, and you'll just keep in a session kind of which stories they say, yeah, hang on to that one for me, and they'll be able to look through a bunch of them, and then at some point say, okay, now print me out all the stories, and you'll just run out a printed version document with all the stories. And that's their class project. People like the project. How are people feeling? I know the planner is probably a step. Next week we have no additional content, no material to be added. We're just going to work on the project because I knew this would be a lot of hours put in, and I didn't want to overburden people. Yeah, I wanted to have a project that was it's a 3-week project. It may take some people. I'm going to introduce it over the next 3 weeks, but you've got till the end of the class to finish it. But I would, certainly try to keep up. But I expect a fair number of people are going to be, still working on the projects at the end of the 3 weeks. I wanted to introduce a project that used a lot of the areas that Prolog is kind of famous for, natural language processing and AI-ish stuff. And this is a very typical little symbolic AI project. I worked on Cogbot for a while, and we use strip splanners all over the place. And I have a friend who did her PhD on linear logic programming, and she now runs a story, a narrative generation lab called the Poem Lab at UNC. So, Chris Martin. So, this is pretty much the kind of thing you see Prolog used a lot for. Okay, I'm going to stick another pause in here, waiting for any final questions or comments, and if not, we'll wrap it up. And I think that's it. Not seeing any more questions. No questions. Looking forward to the project. Okay, that sounds great. Chris Martin, I mentioned that Chris is a Chris's claim to fame before was was doing linear logic programming. That's what she did her thesis on, and self. And then she got a position at the. She became a professor as a postdoc at UNC, she runs a lab there called the Poem Lab that studies narrative generation. And so this would be, this is material was a natural follow-on for her studies in linear logic. And this is the kind of thing that if you hang out on the #Prolog channel on IRC, you will run into a character named Douglas Miles, who is always talking about these kinds of subjects. But yeah, there's a whole there's actually an academic, no, not Chris Martin, the woman. Chrisomophone on Twitter. So there is a whole SIG within ACM on planning. Planning is a huge field. There's a contest every year to study. There's a contest where they put out a planning a thing to plan and see who can plan it fastest. There's conferences and journals, and people make this their academic specialty. And commercially, it's very important. If you can improve the efficiency with which you use a oil tanker by 3%, that may be $100,000 over the course of a couple of years. So it's well worth, using a planner to figure out how to make the most money with your oil tanker or your factory. The origin of this field was World War II. The Robert McNamara and other folks got involved in something called operations research, studying, what's the most efficient way to move a whole bunch of freight down a country, when you only have a country road to move it down, and you have a bunch of trucks or that sort of thing. So, welcome to kind of Prolog's normal corner. Okay, folks. I think at this point we're done. Thanks for showing up. I'll keep the stream running long enough to see if there are any final questions, and if not, we're off.